let's get started. So today we're on to 7B.2 and 7B.3, and it's good we're going to really reiterate those sine functions that we were looking at, the graph of the sine function. If you haven't had a look at Thursday's lesson, you should still be able to access it, and it'll still be a good point of introduction for you. So we should remember the basic sine wave has a wavelength of 2 pi and an amplitude of 1. So what that means is that the highest it will go is to positive 1, and the lowest it will go is to negative 1 here. And that it has a wavelength of 2 pi, which means it's going to repeat itself every 2 pi. We should also remember the wavelength formula, lambda being the symbol for wavelength, is 2 pi divided by b, where b is the coefficient of x. So now we're going to look at how all of these things affect the sine graph. You will have access to your calculator, but I'm going to try and draw these things out just from the properties of the sine function, and they're all stated at the top of our notes there. So let's have a quick look at that. We have a sine of b of x takes c plus d. We have a is the amplitude, all right? And so it is the distance from a peak to a trough divided by 2. It's the distance from the principal axis to a peak or the principal axis to a trough. That's how far the amplitude is. And we know for the basic sine function, if we have y equals sine x, all right, the number out the front here is 1. So the amplitude is 1. Okay, so let's have a look at our first examples then. Here, y equals 2 sine x, the amplitude is 2. Now what that means is the highest that it's going to go is to positive 2, and the lowest that it's going to go is to negative 2. So we'll have a quick sketch of that there. And it still has a wavelength of 2 pi. And so we basically know if that's 2 pi, then this is going to be pi here, and you can divide it up into those kind of segments as well, right? So in between 0 and pi would be half of pi, pi on 2. We can have 3 pi on 2, but that is perfectly sufficient for our first graph. That's the graph of 2 sine x. Next, let's look at 0.5 sine x. Okay, so 0.5, that means half. So this time the amplitude is half. So when we sketch it this time, it's going to have a lot smaller amplitude, right? We have 0.5 to negative 0.5. Still has a wavelength of 2 pi. All right, the coefficient of b we'll look at a bit later, but it's much more squished towards the x-axis. Now we've actually seen these properties before when we were going through exercise 3F, and we were looking how does the number out the front affect a function, and it stretches it and it squashes it. We call that dilation, right? So we've seen that there before. Okay, when we have negative sine x, all right, so the amplitude is 1, right? The number in front of it is 1, but there's a negative there. So let's think like, if we take the basic function here, and I'm going to make every y value the negative of what it is. So that means these y values are going to flip down here, and a negative times a negative becomes a positive. So these y values here are going to flip up here. So when we have the negative of a function, it is the reflection of it in the x-axis. It's going to look like this. Okay? Amplitude is still 1, so the highest it'll go is 1, the lowest it'll go is negative 1. But the negative out the front, all that does is flip it upside down. It inverts it. Okay, let's move on to D then. And now we're moving away from the amplitude and we're starting to look at this B value and how this affects the function. Now we said the best way to think about B is that number B, it tells you how many wavelengths there are in 2 pi. So if we look at this first one, sine x, well the number in front of x is 1. We have one lot of x there, which means there is one wavelength in 2 pi for this first function. So if we're going to sketch this first function, here's 2 pi, and we have one wavelength in 2 pi. The amplitude is just 1, right? The amplitude hasn't changed. We'll have 1 and we'll have minus 1. So that's the first function, y equals sine x. We're also asked to graph y equals sine 2x. All right, so that number there, 2, that tells us there are 2 whole wavelengths in 2 pi. So here's 2 pi, which means halfway is pi, And if we have two wavelengths in 2 pi, it means we're going to have one whole wavelength in pi, and then another whole wavelength, right? So you can see we have 2 wavelengths in 2 pi. All right, maybe I'll sketch it in a different colour so we can clearly see the difference between them. So we'll go black. All right, so we have 2 wavelengths in 2 pi, and the original function only had 1 wavelength in 2 pi. So that's the difference between them. Okay, if we have sine of 3x, this means we're going to have 3 wavelengths in 2 pi. So we've just got to divide it into thirds, right? Here's a third, and so we have 1 whole wavelength there, another whole wavelength there, and another whole wavelength there. 3 wavelengths in 2 pi. All right, and so then each section, this point here, that's going to be 2 pi divided by 3. So 2 pi on 3 would be the x value there. Here it's going to be 2 lots of 2 pi on 3, which is 4 pi on 3. Okay, still has an amplitude of 1, right? That number out the front is positive 1. Okay, sine of half x. This means we have half of a wavelength in 2 pi. All right, so here's 2 pi. We have half of a wavelength there, which means we have a whole wavelength in 4 pi. Amplitude of 1. All right, so in our first examples, we're drawing out how the amplitude affects the function. In our second set of examples here, we're drawing out how the period, how the value of B affects the wavelength, how we can see it stretches it and compresses it in the horizontal direction. All right, so what we should see is that if we have a larger value, we went from 1 to 2 to 3, we're squashing it in. We're squeezing more wavelengths into 2 pi. And if we have a value that lies between 0 and 1, the closer it gets to 0, the smaller it gets, the further apart we're going to stretch it. And I actually just emailed some notes about this to you guys on Friday, because that's going to help you with the roller coaster folio as well, how we transform these functions. Okay, then we're on to C and D. So we have here y equals sine of x. Okay, so the graph, and then plus 3. So that means every y value gets 3 added onto it. We're just moving the whole function up 3 units. So what that would mean is this point here gets moved up 3 units. This point here gets moved up 3 units. So it means here's our x-axis. Our principal axis becomes 3. Now, principal axis is the line about which the wave propagates itself. It goes down 1 unit and it goes up 1 unit. Okay, so there's going to be 4, that's going to be 2, there's 1 there. So it starts here, it's going up 1 and down 1, and it still just has a wavelength of 2 pi. All right, the value of D, this value here, this number here, will always be what we call the principal axis. That is the line, it's an invisible line about which the function propagates itself. It's normal about that line. Okay, so all we've done is we've taken the base sine function and shifted it up 3 units. We can see we still have an amplitude of 1, right? Distance from the principal axis to a peak, distance from the principal axis to a trough. Okay, now sine of x, take 1 in brackets here. This is going to be a horizontal translation, and we tend not to ask these in a test. We just want you to understand how it works. They just get a little bit messy, all right? So hopefully we remember from 3f that if we have x take 1, it's moving the whole function 1 unit to the right. If we have x plus 1, it's moving it to the left. So what that would mean, we've got x take 1, so it means it's picking up sine of x. Here's the function, it's picking it up and moving it to the right 1 unit. Okay, so what that means then, we can think about it like this. Rather than starting here at 0, it starts 1 unit over. It's going to start there at 1. Okay, and then we just have the normal function because we've just shifted it to the right. And so then this point, which would normally be 2 pi, has been shifted over an extra 1 unit. So we can call that 2 pi plus 1. All right, this point here, that's normally pi. It's been shifted over 1 unit. That's pi plus 1. All right. And because it's a periodic function, right, it's going to repeat itself in both directions. So it means it is going to go this way, and it is going to keep going that way. We can just draw arrows to demonstrate that. Okay, so that's H. Now, with these horizontal ones, I reckon when you're moving them horizontally, you can either do what I've done, or you can use your graph to support you. Certainly you can use your graph to support, your calculator to support you. You will have access to your calculator in the test, but I think the main idea is to draw out the concepts from it. What we're going to do now, however, you won't be able to use your calculator for, apart from to check your answer. Lincoln, we're given a graph, and we have to find the equation that describes this graph. So we're looking for all of those features, the value of A, B, C, and D. Now, I think the easiest one to start with, I might just write a list here, A, B. Now, I said we won't really ask horizontal translations, so we can skip C, and we'll just go for D, A, B, and D. The easiest one to start with is certainly D. D is the principal axis. D is the value of which the wave function propagates itself about. So we can see in this circumstance, D is positive 1, that the whole function has been lifted up 1 unit. We can also see that the amplitude is 2, the distance from the principal axis to a peak and from the principal axis to a trough is 2 units. So our amplitude is 2. And the wavelength, the distance for one whole wavelength is 2 pi. We have one wavelength in 2 pi, which means our value of B is 1. B is how many wavelengths are there in 2 pi? There is one wavelength in 2 pi. Okay. On to B. So our principal axes here will be -5. So we'll have A, B, and D. D is -5. The amplitude is the distance from the principal axis to a peak or to a trough, and we can see that that is 5 units. Amplitude will always be positive, all right, because it's a magnitude, it's a size. How big is the wave, right? And then B, how many wavelengths are there in 2 pi? So we can see one wavelength in pi, we have 2 wavelengths in 2 pi, which means our value of B is 2. Alright, so sorry I didn't do this with the first one. Now that we've identified the values of A, B and D, we need to state the equation of the function. So we're just putting in A at the front, so we have 2 sine, and whenever there's just a sine of 1x, we don't need to put the 1 in front of it. So we have 2 sine of x, but then we do have a D value of +1, so it's been shifted up 1 unit. The graph of this function is y equals 2 sine x plus 1. So the only way you could use your calculator to help you is if you were to graph this and identify that they're the same function. So you still do need to be able to identify what's the values of A, B and D in order to graph it anyway. Alright, so in this circumstance we would have y equals 5 sine of 2x, take away 5. Alright, and then on to C. In example C, we would have A, B, and D. We can see our D value is +2. We can see our A value is +3. Alright, so the distance from 2 to 5 is +3. And from 2 to -1, that is also +3. We have an amplitude of 3. And then the B value. The B value here is intentionally a little bit tricky. We're going to use this formula here, all right? Because on this axis, we don't have lengths of 2 pi, all right? In all of these, we very clearly can see how many wavelengths there were in 2 pi. This circumstance is a little bit different. We can't see how many wavelengths there are in 2 pi. So instead, what we're going to do with this one is we're going to say, well, how long is it for one wavelength? What we can see is one wavelength is 4 units long. So what this means is 4 equals 2 pi divided by b, okay, from the wavelength formula. And we can swap b with 4. We're going to perform that algebra. We have b equals 2 pi over 4, or it would simplify to pi on top of 2. So that's the way we determine the b value when we don't very clearly have an axis in 2 pi. We say, how long is it for one wavelength? We can really clearly see one wavelength is 4 units long, so we substitute it into the wavelength formula. 4 equals 2 pi on b, therefore we get b is pi on 2. Alright, so b is pi on 2, so that means the equation of this function would be y equals 3 sine of pi on 2 times x, okay, bx, and then plus d. Really good. So that's enough for us to do exercise 7B.2 and 7B.3. Let's make a start on that.